In this video, I'm going to explain about the coding for triangular signal, which is x1t, and the rectangular signal, which is x2t. So for now, I'm going to explain the triangular signal first. First and foremost, we can use this line of code to generate time vector. For information, these chord lines will create a vector t representing t ranging from -1 to 3 seconds within 1000 points. Next, we need to initialize the triangular signal using these lines. So these lines can initialize a vector x1 with zeros, where the size of x1 is the same as the size of the time vector t. Then, we need to define the triangular signal using these coding lines. The triangular signal, which is x1t, is constructed in two parts. For the interval between 0 to 1, the signal rises linearly from 0 to 2. For the interval from 1 to 2, the signal falls linearly from 2 back to 0. Finally, we can plot the signal based on the chord here. We can know that this chord will create a new figure and subplot, and then we can plot the triangular signal, which is x1t against time. The title, x level, y level are set for the plot. Axis will set the limits for the x-axis and y-axis on the plot. In summary, this chord will generate and plot the triangular signal, which is x1t with specific characteristic over the specified time range. Next, I'm going to explain about the coding for rectangular signal, which is x2t. Firstly, we need to generate time vector. So from this line, we can know that it can create a time vector t2 ranging from -2 to 2 seconds with a step size of 0.01 seconds. The colon operator is used to create a range with the specific step size. Next, we need to define the rectangular signal. So from this line, we can know that the rectangular signal x2t is defined using logical condition. Is 1 when it's true, and the t2 is between -1 and 1 and 0, which is false otherwise. This will create a rectangular pulse that is 1 between -1 and 1 and 0 elsewhere. Finally, we can plot the signal. So refer to this chord, we can know that this chord will create a new figure, plots the rectangular signal, which is x2t against time, and set the title, x level, and y level for the plot. So also for the axis, we'll set the limits for the x-axis and y-axis on the plot. In summary, this chord will generate and plot a rectangular signal, which is x2t, that is 1 between -1 and 1 and 0 elsewhere, over the specific time range. The resulting plot will show a rectangular pulse centered around the origin.
In this video, I'm going to show you the addition of both signals, which are triangular signal and rectangular signal. So actually from here to here is the signal for the triangular signal and rectangular signal. So let's focus from here and here. So this one is the addition for the both signal. Then this figure is, I'm going to create a figure window. So let's run. So a figure window is created. Then from here to here is the graph plotted for the triangular signal and rectangular signal. So let's focus here, which is our addition of signals, zt. Then this 3, 1 for the subplot means that I want to create a figure window into 3 times 1 grid. Then the last 3 here is that I want to label my zt at the position of 3 here. Okay, so I'm going to plot my tz, my title, my x label, and y label here. Okay, so this is the addition of the zt. Then so here are the MATLAB code. Then next I'm going to show you my calculation. So according to the signals given, I have written the mathematical expression for x1t and x2t. Then zt is the addition of x1t and x2t, so I'm going to add both mathematical expression together and I get the final expression here. Then I'm going to plot the graph by using this method. Then this one is my final graph. So as you can see, the graph that I plotted from the calculation is actually same with the graph from the MATLAB code. Okay.
Next for MATLAB coding for task 1 number 3, first of all we define the triangular signal S2T and rectangular signal S1T, and then we define the range independent variable tau and type vector to VCR as you can see in this section. Afterward, we initialize an array to store the convolution result for each time step, and then we iterate through each time step in TBDC. Afterward, we compute the convolution integral with the store the convolution result, and then we plot the S1T and S2T signal with a point for the current time step, which is we include also shade the overlapping region between S1T and S2T, which is what we want to see, and then we use the edge color to use the flash to highlight the overlap, and then we order the plot element to display the shaded region properly in this section, and last but not least, we plot the convolution result over time. So here is the result. As you can see, the overlapping region. Next for the calculation task 1 part 3, we need to calculate yt equal to xt multiplied by s2t by using the convolution operation, and then we need to replace t in x1t by using tau, and then t in s2t by using t minus tau, and then we calculate by using the formula given. Right, so for the case 1, we need to consider that t plus 1 is less than 0, then t less than -1, and there is no overlapping between two signals, so yt is equal to 0. So for the case 2, we consider that t plus 1 is between 0 and 1, so it is between -1 and 0. Since it's overlapping, we integrate from 0 t plus 1, and then we can get the result. For the case 3, we can consider that t is between 0 and 1, as we can see that there is no overlapping. 0 and t plus 1, therefore we integrate from 0 to t plus 1. Alright, for case 4, we consider that t is between 1 and 2, and then from the graph there is no overlapping. T minus 1 and 2, therefore we integrate from t minus 1 to 2. For case 5, we consider that t is between 2 and 3, and there is no overlapping between t minus 1 and 2, therefore we integrate from t minus 1 to 2. And then for case 6, we consider that t is more than 3. Since there are no overlapping, therefore yt equal to 0. So last but not least, we summarize all cases. We can get this graph by using MATLAB code as we see before.
Hi, now I want to explain about task 2 and show the calculation of signal ft and ht using convolution to get output signal yt. For ft signal, our group assigned to do this type of signal for ft, and for ht signal is this. Okay. For ft signal, when we do the calculation, we will get this type of signal for FT. Okay, for HT signal, we will get this. Then after that, we will do the convolution part. And the convolution formula is this, the general formula. For FT signal, we will change T into tau. And then we will get this. And then we time reverse it, we will get this. And then next we time shifting FT signal. And then lastly we will get this for FT signal. And then for HT signal, we change the T into tau. So we will get this. Okay, after change it into tau, we proceed to using this formula. First of all, case 1, that is T less than 0. Yt, we will get 0. So from this, we will see there's no overlapping signal for case 1. Okay, next, for case 2, where T greater than 0, but less than 0.25. So using the formula, this formula, we will get Yt equal to 1.5T. Okay, as you can see, there is overlapping signal over there, which is this area. Okay, for case 3, where T greater than 0.25, less than 1.5, we will get Yt equal to 0.375. And also you can see there is an overlapping signal here. Okay, we proceed to case 4, where T greater than 1.5, less than 1.75. Okay, using the formula, we will get Yt equal to 2.625 minus 1.5T. And from here also, we can see there is overlapping signal happen, this area. Okay, for case 4. Next, for case 5, where T greater than 1.75, less than 2. We will get Yt equal to 0. So there's no overlapping signal here happen. Okay, for case 6, where T greater than 2, but less than 2.25. Using the formula Yt, we get 2 minus T, where from here we can see there is overlapping signal over here. Okay, that is for case 6. Next, for case 7, where T greater than 2.25, less than 2.5. Using the formula, here we substitute inside this, we will get Yt equal to negative 0.25. Okay, from here, so we can see there's overlapping signal happen, which is here. Now for case 8, where T greater than 2.5, less than 2.75, we will get Yt equal to T minus 2.75. Okay, also there's overlapping signal here. Okay, last is case 9, where T is greater than 2.75. For this case, Yt equal to 0 and there is no overlapping signal happen. Okay. So the calculation part to get Yt is done. Okay, for the calculation, we put all the values that we get into a table. Okay, from this table, when we substitute the value of T into all of this function, we will get the values for Yt that we need to plot on the graph. Okay, for the Yt, we start from range 0 to 0.25. So from 0 to 0.25, okay, we will get the Yt 0 to 0.375. So we substitute 0.25 into 1.5 times 0.25, we get 0.375. Okay, next, time range from 0.25 to 1.5, we will get 0.375. So it will maintain 0.375 from T 0.25 to T 1.5. Okay, next, range from 1.5 to 1.75. Okay, we substitute 1.5 and 1.75 into this function, we will get 0.375 to 0. Okay, next, range 2 to 2.25. We substitute this value into 2 minus T, we will get 0 to negative 0.25. Okay, next, range 2.25 to 2.5. We will get negative 0.25. So from this range, for this range, we will maintain negative 0.25 here. Okay, lastly is range 2.5 to 2.75. We substitute this t into this function, where we get negative 0.25 to 0. Okay, so that's how we get the output signal for Yt. So this is the output signal for Yt.
I'm going to show the MATLAB program of the convolution task 2. First, we clear the window, combine window, and open a new figure window. And then we define the function of input signal ft and response signal ht. And this is a function of the ft, and this is a function of the ht. And then we define the trial time vector from negative 1 to 4, the step of 0.01. And then we initialize the index for the time vector, which t initial equal to 0. And we define the t time vector from negative 0.5 to 3.5 with a step of 0.05. And then we initialize the output y with not a number values. This is a formula. This that we initial the output y is 0 first. And this is a for loop for the time vector t back. For t equals to t back, the time index increased by 1. And this is the formula of the convolution operation. And we need to perform the convolution of function f and h with respect to tau, where t is the current time. And then we calculate the integral by approximating the Riemann sum. And then we plot the ft and ht graph in the first subplot. So we begin to run the graph. This is the ht graph, the bigger graph, and this one is the ft graph. Then this is a overlapping gradient process, and we order the children of the graph to place the patch behind the curve. And finally, we plot the integral convolution graph in the second subplot. And we update the figure window. So this is the second subplot, and this is also our convolution graph, final convolution graph.